So we're going to talk about Boolean algebra and reduction techniques. So again, for the logic review, we have different symbols for and. It looks like a D. For or, it looks kind of like the looks like the Star Trek symbol if you really want to go with it. NAND. The way we know it's a NAND is because of this little circle right here. Same for NOR, and then for NOT. NOT's kind of the same thing. So in order for it to be labeled as not so much reverse or negative, but so for these three right here, what you should know is that this means it's reverse logic. So instead of all highs equaling a high, as long as you have any low, you get high. Does that make sense? All right, I'll take that as a yes.
Wait, you said as long as you have any high, it's a high?
No, I said any low equals high.
Oh,
I'm sorry. No, that was right. It's any high equals a. I'm getting myself confused here. So for AND logic, you have to have two or more inputs that have come together to get an output. Let's kind of go back to that. You have to have two inputs that are good to get an output. However you want to put that. With OR logic, any high or any signal is a good signal. Means it allows for that flow and for everything to continue. However, with NOT logic, so let's look at NAND. So if you have to have two highs to get an output on AND, for NAND, all highs equal, you have to have two highs to get a low. Okay, so if I was to draw this out, so for this guy, you have to have X and Y to equal Z. Try that again. So you have to have X and Y equals Z. Okay, so if you remember the truth tables, I don't know if I can draw them real well. For this guy, on a truth table, if I can get this thing to work for me here. So if I have one here, nothing here, this guy has nothing. If I have nothing here, one here, this guy still has nothing. In order for him to be on, he has to have two inputs to get an output. For NAND, it's just the opposite. So for NAND, anytime you have an input, you get an output. Unless you have two inputs, then you get no output. This guy is also true if you have no inputs at all. This guy won't turn on if you don't have some form of a dual input. So think about it almost like tug of war. Okay? Can't have one for tug of war. If you really want to kind of think about it this way, this might be an interesting way to kind of present this for y'all. In tug of war, can you play a game of tug of war with just one person? Or one team?
No.
No, you can't. It cannot be done. So that's where you have, so this would be team 1, team 2. I have to have 2 teams to get a game. Does that make sense? Or you could even compare it almost to football. Right? You have to have 2 teams to create the game. Make sense? So for NAND, you can think of it like this. There can be no winners or there can be one winner of the game. But you cannot have 2 winners in the game. Does that make sense? Somebody has to win, somebody has to lose. Yes, go ahead. Do you have a question? So that is and NAND logic. You have to have 2 teams to play the game for and logic, but only one team or no teams, if it comes down to something like a tie, then you have no winners, but you still get a game. For OR logic, okay, so if we're going to go back and do a truth table for OR logic, OR logic states that any input gives me an output. Okay? OR logic tells me that any input will give me an output. Okay? So what would y'all think to equate this to? Anybody at all? So the best way you can equate this to is if I'm looking for, if I'm starving enough, then any food is food. The only time food is not food is when there is no food. Does that make sense? I'll just kind of put it in kind of semi-basic terms here. For NOR logic, though, we go back to the truth table. I don't know why it keeps doing that. For the truth table here, any time you have an input, you will not get an output. The only time you're going to get an input is if there is nothing there. Okay? Y'all are all very quiet this morning. And then not logic is basically what it sounds like. Basically, anytime you get a signal for yes, it outputs a signal for no. Anytime you signal a no, you get a yes. So he is literally opposite day. Okay. Everybody good? Anybody got any questions? Any questions at all, guys? Speak now, please, or hold your peace. Okay. Just trying to make sure. The combination logic is using two or more logic gates to form more useful functions. Okay, so this is where things kind of get interesting, simply by virtue of combinations tend to be very interesting with a lot of stuff like this. And that's what we're going to be talking about. So if you have a combination of logic functions, so you have b is equal to kd plus hd. So the Boolean reduction is b is equal to d times the adding of k and h. Okay, let's just make a little more sense here soon. So if you think about your car, what can lead to the warning buzzer is, let's say you get in the car and you don't have your keys in the ignition. Will the car start?
No, ma'am.
All right. So if you get your key in the car, you get in your car. What do you always have to do before you can crank your car? At least 90% of car models, you have to do what?
Put your foot on the brake.
You have to put that foot on the brake. Make sure that brake is matched in before it will allow you to crank the car, right? Sort of like if you're trying to shift gears from reverse to whatever first, second, whatever gear you need to be into, you have to press that brake. Okay. So something as simple as the headlights are on and the door is open. can send off the warning buzzer in this case, or the door's opened and the key's in the ignition. At which part your car starts fussing at you. Excuse me. Right? For instance, I can remember whenever I was a kid, we had this car that anytime you left the door open, it would actually tell you your door is ajar. And it would keep repeating that over and over again until you wouldn't close the door. Once you closed the door, it stopped. So that was its warning buzzer. What's something that you have to do before you put your car in drive, or what you should do, rather? Is you have to put on your seatbelt, right? That causes a little warning sign to go off on your computer. Causes a warning signal to go off on your car till you put that on. Why it keeps going ding, ding, ding until you sit there and click it in, then you have your car able to run. All of that can be done through logic gates. But this can be reduced to where you have an AND gate here. So if we're looking at this guy, we have two AND gates and an OR gate for this logic. And both of them include this guy right here. The door is being opened. The only differences are one has the headlights on, one has the key in the ignition. So to reduce that, we take an OR gate for our key in the ignition and our headlights, and then tie that to an AND gate with our door being open. Does it make sense to everybody? So being able to simplify something like that would be very useful in automation, right? Because what's one thing we don't want on the floor with automation? Well, you definitely don't want water, but you don't want a whole lot of clutter. Because more clutter means more things that the drivers have to get around on their forklifts, and it just keeps snowballing into bigger and bigger problems. Most corporations want to keep their floors clear and clean just so that they don't end up having people knock into each other or knock into product. Okay. So for this one, so let's talk about this like it's in a bank. So again, we've got two AND gates, and we've got ink all over the slide apparently. Or not. Anyway, so you have after hours. So it's basically what it's saying is, hey, the doors are closed. It's closed for the night. So we have after hours. And then we have the vault door being open or the front door being open that causes the burglar alarm. Because we don't want people just randomly walking into different places where we exist and running off with the stuff we want to have there. Right? So if it's after hours, one way I can write this again is that I go back to this AND gate tied to a NOR with a NOR gate. The OR gate is saying the front door is open, it's after hours, sound the alarm. This is where you have to set alarms and say, you know, we're closing up for the night, so turn on the alarms, make sure nobody just kind of randomly walks in, right? I don't know how many of you have ever worked retail, but that is pretty much what happens when they close down every night. Is everybody turns off the lights, you make sure you set the alarm on the way out so nobody just randomly walks in and starts taking stuff. for this one, so after hours, if the front door opens, it sounds the alarm. If the vault door opens instead, it sounds the alarm. In case somebody just happened to have been able to stick around and not get caught, make sure that you still end up without them getting away with stuff. Okay. So what about this one, guys? Do you think this one could be reduced? What do y'all think?
Yes.
Well, probably not by much, but we can expand it out. Um, in this case, we have A, B, C, D, and E. So I don't know how many of y'all remember going over this in intro, but you have things like the cumulative law. I'm sorry, the cumulative. Apparently, I can't talk today. Commutative of law of addition. Basically, what that means is what? As long as I'm only adding the numbers, I'm not performing any other option, what can I do?
You can reverse them.
Not just reverse them. What I can do, and this is the kind of the cool thing about it, is the fact that when I'm doing that kind of mathematics, as long as I'm strictly dealing with addition, if I have multiplication, division, or subtraction thrown in there, I've got to account for those and this doesn't work. But with addition, strict addition, I can add them in whichever order I want to. Does that make sense? So if I had a string of numbers, let's say I was adding 10 to 20 plus 35 plus 42. I don't have to do it that way. I can add 42 to 10 to 35 to 20, so on and so forth. And I can do that a million different ways as long as I'm strictly doing what?
Adding.
As long as I'm strictly adding. The second another operation enters the equation is whenever that will no longer work. Does that make sense to everybody?
Yes, ma'am.
Okay. The associative law of addition means that it doesn't matter if it's in the parentheses. And again, this only applies when you're strictly doing what? When you're strictly working with addition. Um, once you've entered into something else like subtraction, multiplication, division, any of those, this law can no longer apply. But if you have nothing but an addition problem, then yes, this is what applies. You can add it in any order, doing any kind of technique you want to do. And then you have the distributive law, which is where when you're multiplying something in parentheses by something outside it, you can pull this apart by multiplying a times b, and then a times c. Okay. Okay, so A plus B is equal to B plus A. A times B times C, or signal A plus signal B plus signal C, is equal to BCA. Somebody messed with that picture. Is equivalent to BCA. It doesn't matter which way you put this, as long as your function is the same across the board. Does that make sense? Okay. So for this guy, again, all you're doing is saying A plus B, then plus C is going to equal X. Doesn't matter which way you add all these, they are all going to add into the equation similarly enough that it allows you to move through it. Okay. All right, so again, as long as your what does not change, as if you're adding. Now this one's a little bit different. Why? Because we have A times B plus C. We saw that just a minute ago in that equation, yeah? So the way we solve something like this would be to say, well, this is also A is equal to B, X is equal to A times B plus A times C, because A is that outlier, which allows him to come back and do something different. Now, figure 512 is interesting. What does it look like for y'all as to what's going on? What's going on with D, guys? Somebody speak up.
Like just combine them. We have x equals AC plus AD plus BC plus BD.
Okay, so if I was to put this in a computer, just to kind of give you perspective as to why this right here is working the way it is. What I'm putting in the computer and running is the fact that if A signals, this guy goes. If B signals, this guy goes. If both signal, this guy goes. Then down here, I have to either hit C, D, or both to get whatever's going to happen. So
essentially, you just need one from each side to go off.
Yes, because they're both OR gates, right?
Yeah.
That's exactly right. You have to have one from each side minimal to make it everything go true. Does that make sense?
It's kind of like when we were in PLCs, me and Chris wrote a program and Rich told us it was wrong and it was actually right, but we did it completely different.
Okay. So yeah. So A can be paired. So the way they're looking at this is that A, this guy right here, will eventually end up paired with either one of these. Right? And then you see that B can be paired with either one of those. Or you can even go backwards and say C could be paired to A to B, or D could be added to A and B. But you essentially have to have a minimum of one signal from each to make this gate right here open. Okay? I have to have a minimum of one from each side because that would be activating the OR gates, which would then your signal to your AND gate. So what would something like this be useful for? What do y'all think?
Two-button start.
Two-button start would be a good one. So what you're saying is you'd have to have.
Well, if you had two people working on the same machine and the buttons were on opposite sides of the machine to make sure that they were clear.
That actually would work pretty well out. I never actually thought of that particular example. But yes, if you have two people, they have to both be outside the cell pressing the button at the same time to move the work to the next stage. You could use this as a safety circuit as a matter of fact. Okay. So some Boolean laws and rules. So rule 1, anything ANDed with a 0 is equal to 0. So anytime you deal with an AND gate, a 0 equals 0. Why does this happen? Well, because going again back to what is AND logic, right? And logic, what do you have to make the signal move through?
Two inputs.
You have to have a minimum of 2 inputs to open an AND gate. So in other words, for an AND gate, think about it like a gate at a concert. You know, some things can go in and out, but until they open both gate doors, most people are not getting in, right? So until both doors become active use, then it's just going to sit there. Does that make sense? Okay. So rule 2, anything ANDed with a 1 is equal to itself. Okay. All right. Then anything ORed with a 0 is equal to itself, or 0 is and then anything ORed with a 1 is equal to 1. Any questions so far, guys? All right. So this one is talking about figure 514. Anything ANDed with a 1 is going to become true. Okay. So essentially, again, this is just looking at AND logic versus OR logic versus NAND and NOR. Okay. Any questions on that, guys? All right. Y'all want to take another break? Give y'all about 10 minutes. Let this kind of settle in your head.
Yes, ma'am.
All right. Yep. All right, so let's talk about a few more laws and rules. So again, a lot of what we're dealing with is the logic. So that's things like and, or, not, NAND, NOR, and how they're going to interact with each other. So for rule 5, anything and with itself is equal to itself. So it's talking about this guy right here. So anything and with itself is equal to itself. So if you have two signals that are the same, they will equal a signal out. Okay. Anything ORed with itself is equal to itself. So right here, anything that is, sorry. So anything that is ORed to itself is going to equal out. Now if you notice, we're starting to use NAND and NOR with this. Pay attention to those guys. So then you have anything and with its own complement equals 0. So that is if and plus NAND, they're going to cancel out. Anything ORed with its own complement equals 1 because you're dealing with OR and NOR. So and plus NAND gives you 0. Easy enough so far?
Yes, ma'am.
Okay. So anything complemented twice will return to its original logic level. So in other words, in this case, you cannot subtract a negative, so thus you then end up becoming a positive, right? So what they're saying is if I take a signal A, I invert it through a NOT gate, then I invert it. So A is equal to A. It goes through a NOT gate to equal negative A, or the inverse of A. When that goes through another NOT gate, it's going to equal out back to its original state. Does that make sense? Kind of, sort of. So A plus the inverse A times B is equal to A plus B. Okay. So here's a truth table to prove the equations we've been working with so far. So we start off with signals A and B. So for the first table, we have A plus the inverse of A times B. A plus A is 0, B is 0, you get a 0. And the same as if you do A plus B. if I'm looking at A and B, and I have a signal at B, that means I get a signal all the way across. So this is actually looking like the equivalent of what? What kind of logic am I actually performing here? What logic allows for any signal to equal in to equal a signal out?
Is it and?
Not and, it's the other one.
Is it NAND?
In this case, it's OR logic because any positive signal is going to give me a signal out. NAND logic would mean that from here up, these three sets right here would give me a signal. AND logic, I'm going to just change the colors of this one. So this would be for AND logic. This is what would give me a signal in AND. See if I can do an AND for SAND. And then this is NAND. All these would give me a NAND signal. These singular ones down here would give me an AND signal. If I was looking for an OR signal, that means I would look at these guys right here. And if I'm looking for a NOR signal, I would look at this one right here. Does that make sense? Does that make sense to everybody?
Yes, ma'am.
Okay. So that is the difference between these. Now, what I'm seeing, I don't know about y'all, but in these two tables right here, these right here are looking like OR outputs, right? Because for OR, any input gives an output, correct? Okay. So then looking at these over here, they're using another truth table. And that is looking at basically, so when A is at 0, I'm going to get a signal. When it doesn't matter what state B is in, if A is at 0, I'm getting a signal. And that works up until this guy right here as a general thumb. Once you get here, it's actually looking at the signal from B. Okay. The signal from B counteracts the signal from A, and you get a outcome. Does that make sense? Okay. So the laws versus the rules are laid out here. Do you have any questions on any of these or what we've gone over at this point? Okay. So equivalent circuits can be formed with fewer gates, so you reduce cost. Why would that be a big thing? Why are we looking to reduce cost?
In case something breaks, you don't want to take a whole big cost out of the company.
There's definitely that. Initial costs are also a big thing because what do people not want to do? People don't spend more money than necessarily, yes. That is a big thing for most people. I don't know about y'all, but not 99% of the world, if they can find it cheaper elsewhere, they're going to. The 1%ers or whatever you want to call them, the uber high rich can afford to throw money around if they really want to, but for the most of us, I think we all tend to live a little more towards modest means. So keeping costs down is a major thing when we're trying to design circuits and such. The more often you can keep the cost down, the better off you and your customer are, because that is what allows for repeat customers. Kind of like for a cell phone. Does everybody get a new cell phone every year? No, because those things cost crazy. So if we can find some way to drive that cost down, either by offering a cheaper version or what have you, then you're up a better creek than your competitor, right? So by using fewer gates, we also increase reliability. There's one less thing to break. There's one less signal to become messed up. Right? Okay. So we like reliability. We want to keep costs down because it means that more people buy the product whenever costs are low. Reliability is always a big thing. I don't know how many of y'all remember the old commercials where, or even just the old times when cell phones were, the signals on a cell phone were crap. And that's when you ended up with the, can you hear me now? How about now? Can you hear me now? Nope, still can't hear you, Bob, because the signal stinks. Because the reliability of the signal was what? If you went 2 feet to the left, you ended up losing your signal, right? Anybody remember that? Okay. So for a warning buzzer, so we get a couple of different ways of doing this, or a couple of different ways that they've set this, or this is the way they've set this up for a logic circuit. So you have a warning buzzer. So we're looking for one of two ways we're going to trigger the signal. So starting right here, we've got an OR gate. So an OR gate's going to take whatever signal it can get, and it's going to tie it back in to use. So anytime it gets a signal, what does it do? So OR gates, any positive So OR gate, any signal in is a signal out. So looking at what is connected to that OR gate means that I'm looking for one of three signals. So if I'm looking for a signal from B, then I'm looking for a signal from A more than likely, because C is going to bypass the whole thing. Does that make sense?
Yeah.
Okay. So since C is bypassing the whole thing, yes, its signal can trigger B as long as B is active. However, if B is not active, C is going to trigger the warning buzzer anyway, so thus that is how that is tied. Excuse me. However, for A to give a signal, it has to combine itself with B. If B wants to give a signal, it has to combine itself to A or to C. Because this is an OR gate, this is an AND gate, which means it has to have two signals in to give a signal out. Everybody see that? Are there any questions on that? All right, so what about this one? That's kind of a simplified version of the one we just looked at, right? In this case, we don't really care. Well, let me back that up. So for this one, C has the ability to activate with B. For this one, C can act on its own just like it is. We don't have to wait for it to get a signal from B in order to activate that AND gate. Instead, this is a little simpler, right? It would take one less component and it would be that much easier to it'd be a lot more reliable, right? One less thing to go wrong. Yeah? So in this case, what they've done is switch up so where A and B are now part of that one AND gate. I don't have to worry about C coming up and putting a signal in here. C's got its own little set of the circuit. So A and B have to come together to make to make the AND gate true. Once the AND gate is true, the OR gate will trigger and the warning buzzer will trigger. C can trigger the gate all on its own. So just like your car. So your seatbelt can, not wearing your seatbelt and having pressure on a seat can cause that seatbelt light to come on, and it sends the signal of, hey, somebody's not wearing their seatbelt. Somebody's not wearing their seatbelt, bugging you again and again and again until you put your seatbelt on, yeah? Would everybody agree with that?
Yes, ma'am.
However, isolating C, so this could be very well just be your car door being open. That's sending off a warning buzzer in your car. So this would be a little bit easier to A, to wire, and B, be a little bit easier to follow if you have to go back and start looking for where is the problem with this particular component. All right, here's one that's really complicated, but it's really not. So we have three signals. Once again, we have A, B, and C. A will, if A trips, it's going to trip off X no matter what it does, right? Now, looking at the next signal, so let me kind of see if I can get this to highlight. Just kind of so we can kind of follow this. So signal A, no matter what, it's going to trigger it. This is where the path that signal A can take. It is the easiest path signal A will take. It doesn't have to wait to go through the OR gate, then the AND gate. It's just going to go straight through and send off the signal. So then looking at B, if I start tracing B, if I start tracing signal B, he can go through the OR gate and into the AND gate, but he's also going to bypass down to this AND gate right here, at which point he's going to have to wait for C to get that signal. But in any case, he's going to have to wait for C because C and this guy don't trigger until C triggers, and then you end up with your signal for this guy right here. And then once that guy comes together, then they can go trigger X. So what's something I could maybe do to simplify it before we kind of take a look at what their resolution is? Wouldn't it be easier to just leave the signal at A? Because the A signal doesn't do anything. It's just kind of out on its own, right? So instead, we could bring B and C together to one AND gate, right? Be a little bit easier. And that's exactly what we would do. So now we've simplified it from this spaghetti run that doesn't make any sense as to why you would use that many extra parts, right? You see what I mean?
Yes, ma'am.
And then we would go to something like this. Hey, that's much simpler. A has its own signal, just like here, because here A does not have to go through that OR gate to get to the AND gate. All it has to do is just go straight to the OR gate, and it's done. It does its job. For B and C, then, we have the AND gate, which is exactly what we were seeing here. B would have to go through at least one of the two AND gates to get a signal out. Here, they're both just tied to one single AND gate, and they're done putting the signal through. There's less things that can go wrong, less places for that signal to get lost or for voltage to drop. Does that make sense to everybody?
Yes.
Have I confused anybody?
No, ma'am.
Okay, just trying to make sure. I hate for anybody to sit there and look at me thinking, dear Lord, what is she saying? All right, so I'm going to give y'all just a minute to look at this one and try and trace it yourself, and then we'll kind of go through it. So I'm going to give you just about 3 minutes or so, and then we'll kind of go through it together, and we'll walk through the highlighting. All right, so starting to trace this, let's start with signal A. So signal A, the way it's going to end up having to work, has to go through this OR gate first. So if it triggers that OR gate, it's going to come out here. We're going to end up dropping down to this AND gate. So I'm going to leave it right there for a second, and then we're going to look at signal B. So signal B has one of two options. It can come in through this inverter, okay? And then it also goes up to this OR gate. as well as down to this AND gate. If it goes to the OR gate, again, it's going to go down to this AND gate. If it goes through this inverter, that also ties this AND gate, as well as coming to this OR gate. And then finally, number C is just coming to this AND gate. It's got to wait for a signal from B before it can come out of come out of this gate and come up to the OR gate. Okay. And so from this AND gate, we also have to wait for a signal from B and from A to get to X. Any one of these three signals will trigger. Now, the interesting thing about the signal from B with this inverter, right? This is an inverter. So that takes a positive signal and makes it negative, or takes a negative signal and makes it positive. So it's going to depend on how you trigger it as to what signal is going to be pushed through and into this AND gate. If I put a positive signal into the inverter, I'm going to get a signal that turns this guy right here off. If I turn B off, it puts a negative signal here, and then this guy will trigger directly. So is there a way we could simplify this? What do y'all think?
Take out A.
If you take out A, pretty much, yeah. So A really has no effect at all. I mean, if you look and follow the signal for A all the way down to this right here, he has no use. He can't get through that AND gate. However, if I just strictly look at B and C, then the things I have to deal with are an inverter and an OR gate. I can drop the AND gate. Does that make sense? So I can go from this tangle of a mess to something much more streamlined. And I lose, let's see, 3 gates and go down to 2. So if I have a signal for C, I'm going to get a signal out. If I have no signal for B, I get a signal out. If I put a signal at B, but not at C, I will have no signal because this guy's an inverter. So again, what does that mean?
Changes its negative.
It changes its nature. So if you give it a 1, it's going to make it a 0. If you give it a 0, it makes it a 1. Does everybody kind of understand that? Now, a lot of this will become clear once we get into lab, and y'all actually get to start playing with the inverters. They're actually kind of cool. But A right here is just useless, so you might as well just take that signal out and deal strictly with the other 2 signals you're having to use. Does that make sense? Does everybody kind of understand where we're going with this?
Yes.
Okay. All right, so I'm going to let y'all look at this one for just a minute, and then we will discuss it again. So, like I said, I'll leave y'all to look at it for just a minute. I'll give y'all till 11:15, and then we'll look over it together. So I'll give y'all just a minute to study this. All right, so let's take a look at this one. So what's going on with the signal for A?
Going into the OR gate.
All right, starts off going into an OR gate, which means that it doesn't matter what signal goes in, the signal's going to come out, right? So then it's going to flow down to this AND gate. We'll leave it right there for a minute. So let's take a look at our friend, the signal for B. So I've got it, first of all, it's going to start coming here. Now what's going to happen? Well, it's going to split. It's going to go here. It's going to come down to this OR gate, as well as going all the way down here to the AND gate out. Okay, kind of interesting how that guy's set up. So let's continue looking. So he goes to this OR gate. So then let's take a look at signal C. C comes in and feeds this OR gate. As we know, anytime you start one thing in an OR gate, it comes through. That includes our reg signal for B. So either one of those signals will make a signal true. Okay. So at some point, two signals have to converge to this AND gate to trigger this guy. What is the main truth here is the fact that B has to be on at all times to allow for that. Right? So let me ask y'all this. Those of you who have ever taken blueprint reading, especially with me, or if you've ever had to deal with schematics, especially with me, taking a look at C and where it crosses the line here, is C connected to the other end of this, or is it on its own, or is it does it feed this line right here, or is it strictly on its own?
It's on its own, ain't it?
It's on its own. It does not feed this AND gate except through this OR gate. Does that make sense to everybody?
Yeah, because it's not. There's no connection point.
Exactly. So if what I'm looking for, I'm looking right here versus right here. Here I've got a connection point. That's what that little black dot means. That's a connection point, which means that this wire right here, this signal from B, is feeding all three of these wires. Signal C does not have that connection dot, which means that that wire is either laid over or under the wire from B, and it does not feed to the AND gate. Okay? So far we got a spaghetti puzzle here. So if C triggers, I also have to have A trigger so that I can get a signal out here. So I can get a signal here.
So would you put like A and B together?
Now that's the funny thing, is that B has one of two signals it's using. It's got an inverse signal here. So what that means is that anything positive becomes a negative, right? Just like anything negative would become a positive. I did not mean to erase all that, but so we've got this inversion gate here. This guy is what kind of starts messing with some things, because if I put a signal at B that means I will not get a signal out. So if I have a positive signal, I get no signal out, right? If I put a negative signal in, I'm going to get a positive signal out. That's the whole point of an inverter. So this guy needs a positive signal to push this signal through. So I have to put a negative signal here. If I do that, that means that this gate cannot trigger, because this gate has to have two positives. This guy has to have two positives to equal a positive. This guy takes a positive and makes it a negative. So that means that this cannot flow through here. So technically C, if we really get down to it, so the way they're simplifying it is strictly putting it through an AND gate and not using C as a signal at all. So why? Well, because the only place C comes through is this OR gate to an AND gate. And then you have all this other garbage up here. The very simplest I can make it is by strictly putting A and B to an AND gate and leaving C out of it altogether. Does that make sense?
Yes, ma'am.
Because if you look here, C is serving no real purpose unless you have A going.
So essentially with all these ones that we've been doing, we're just trying to put it in its simplest form.
Yes. Because the simpler it is, the less parts you have to use and the less things can go wrong. Think about the most complicated machine you can ever think of. How many points can it go wrong? Right?
Everything you add into it.
Everything you add into it is another place where it can go wrong. So the fewer things you throw into the mix, the less problems you will have at the end of the day. That's why a lot of things have become very simple. If you actually open up most circuitry, you'll find it's not as complicated as you think. And that is simply because it creates fewer points of failure that will rile up a consumer, right? Does that make sense to everybody?
Yes, ma'am.
Yes, ma'am.
All right. So positive logic, kind of just doing a review here. So the positive symbol is an AND symbol. So all highs to equal a high. I'm going to add that in. You have to have all highs to equal a high. So again, that truth table means that this has to activate and this has to activate with a positive signal to get this to activate with a positive signal, right? For an OR gate, any one of the two inputs, plus, if it has 3 inputs, 7 inputs, I don't care. Any one of the inputs creates an output. So that was why any high equals a high. All right, for a NAND gate, the NAND gate is opposite of the AND gate. Right?
Right.
So that means that if all highs equal high to an AND gate, that means that if I get all highs, if I get 2 highs here, that means this guy goes low. That means he turns off. Which means that as long as there's a 0 somewhere hanging out on here, then this guy's positive. Does that make sense?
Yes.
Yes, ma'am.
As long as I got that 0, I can get that positive. For this guy, he wants no signal from either place to get a high. Okay? So if this guy's demanding a signal somewhere, some way, somehow between these two legs to get a high, then this guy wants no signal whatsoever to get a high. Okay, to get a signal through. Then for a NOT gate, positive. A positive signal becomes negative, or negative signal becomes a positive. That's why this is called an inversion gate. It quite literally takes whatever signal you put in on it, flips it on its head. Does that make sense?
Yes, ma'am.
Okay. So looking at this, we have what's called De Morgan's theorem, and that is that every AND has an OR function and every OR has an AND function. So this basically is where the NAND and NOR gates come in. Okay? So a NOR signal is equal to I'm trying to think about how to say this correctly, but my words have been failing me today, so sorry guys. So this guy is essentially saying that NAND and NOR gates can be simplified to AND and OR. So again, if you're looking at truth tables, so this is one, so signal 1, signal 2, and output, right? So if I go in and say we have 0, 0, 1, 1. Sorry about that, guys. Some reason my computer decided to. Sorry. So 0, 1, 0, 1, and then 1 to 1, right? This is our basic truth tables. So if I'm looking at AND, this guy is going to give me no output. This guy gives me no output. This guy gives me no output. And I get output here. If I'm looking at NAND, I'm looking at the same truth table. I get an output here, 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 no output here. Making sense so far? If I'm looking at OR, I don't get a signal here, but I get one here, here, and here. And then lastly, looking at NOR, I get a signal here, but not here, here, or here. So what does this mean for me? Well, that means that the opposite of AND looks a lot like NOR. And the opposite of NAND looks like to be NOR. But all this is saying is that these four are very closely entwined. Does that make sense to everybody? Kind of, sort of. Now this kind of makes a mess. I don't know why it keeps sketching out like that, but let's see if it'll let me clean that up a bit. So this is the truth table as it is, guys. So for AND, the way to get an output, you have to have two positives. The opposite of that is NAND, where you have to get a 0 in at least one place to get an output. For OR, you have to have, it's the same thing. You have to have a signal somewhere. You have to have a 1. For NOR, you don't want any signal whatsoever. So what they're showing you here is that they're breaking the bar over the symbols in order to break these up. So, and then what you add here, you multiply here, and what you multiply here, you add when you break them apart. So when we're looking at these theorems, you're breaking the bar over the variables and change the sign between them. So we use inversion bubbles to show inversion rather than inverters. So if we're going to invert a signal, let's say we use a OR gate. I'm really sorry, this is not going to look pretty, but the way we show inverting, we can invert the signal here on entrance, or we can invert the signal on the exit. And we do that instead of using inverters. Okay. So all this kind of makes sense for y'all guys? Okay, so if we invert So if we take an AND gate and invert the signal on the output, we get the same thing as if we invert the signal on the input of an OR gate. Like I said, a lot of this will make a lot more sense when we get to actually work with the components. And I'll get to see exactly what this looks like. So a NAND gate, that's exactly what this is, looks like an inverted OR gate. It's where you invert the signals on the OR gate. You'll see that? So then we look at this guy. So this is a NOR gate that is very similar or exactly the same as this inverted AND gate. Again, what we're inverting is that signal on the very beginning. Okay? So an OR gate is a completely inverted AND gate. So if I was looking here at this truth table, this would be a 0, this would be a 1, this would be a 1, and this would be a 1. So if I look at this guy, then that means that I should get a 0 when I put no signal in. I should get no signal out because there's nothing to invert. Put a signal in, I get a signal out. I put a signal in, I get a signal out. And I put 2 signals in, I still get a signal out. And then the only place I should get a signal out is where with this, guys? Where should I expect to find a signal here?
Where A and B are both 1.
Yes, so I should not expect to see a signal here. This is an AND gate again. You shouldn't expect to see a signal until you get both signals into a signal. That doesn't make sense. Unless the only time you should see a signal is when both A and B send one. For this one, you should not see a signal either until you get to the point where both are putting signal in. So essentially what this is saying, well, here's my positive signal, this guy turns it negative, and then this guy takes the 2 negative signals once they come out and turns them back positive. Does that make sense?
So like the reason like you would use these like with inverters is just because of the way it's done in the essentially whenever you put it into like a parallel circuit, right?
Yes.
Because everything else on that circuit would run negative instead of that one.
Yes.
So do you need another inverter on the way out, or?
In this case, you would be using something along the lines of a NOR gate, but you would invert the signal on the NOR gate to get the other result. So let's say all you have lying around is a NOR gate, then this is how you would end up getting a positive signal out of a NOR gate. Does that make sense?
Yes, ma'am.
All right. So looking at this, so if I get a positive signal coming on A and B, that means I'm going to get a negative signal out. C and D, same thing. Positive signal is going to become a negative symbol. So then once it comes to the NOR gate, I'm going to end up with an inverted signal that's going to come out positive. Okay? Does everybody see that? So if we're going to ease circuit simplification, so that's what they're doing here at B, you've got your original circuit. So let's simplify it out. Well, they say let's invert the signals from C and D to make this a NOR equivalent by making sure that the signals are an invert to this AND gate. So the inversion bubbles will cancel and I'll still get my positive outcome. So essentially this ends up becoming 3 AND gates. Does it make sense? What they're trying to show you guys is that the negative symbol or the negative signal essentially ends up where these inversion bubbles are. And what they're trying to do is simplify it out so that you don't end up with anything overly complicated. Because all these bubbles mean is that you're inverting the signal from what you had before. So just like an inverter, if I've got positive on this side, I've got negative on this side. This one, if I've got positive on this side, I still get negative on this side. So whatever the signal coming in, this is the opposite coming out. So I put 2 negatives into an NOR gate, I get a positive that comes out. Does it make sense?
Yes.
Okay. So we have what's called bubble pushing. This is a shortcut method of forming equivalent gates. It's what allows us to change the logic of a gate. So if we take an AND gate, this is what allows us to change it to an OR gate, or change an OR gate to an AND gate. Okay. So I can take an AND gate and turn it into an OR gate by putting inversion bubbles. And you can see them doing this the whole way through all this. So all that means is we're inverting the signal from whatever we had before to a new signal now. Basically, they're just trying to show y'all some different ways that you can use to create an AND gate and move it into use like an OR gate, or taking an OR gate and moving it into a use similar to an AND gate. Like I said, a lot of this will make more sense once we get to lab. So the capability of NAND and NOR gates. So if you combine one or more NAND, you can form any other gate you need to, as well as for NOR. But you can't combine NAND and NOR to create another gate. Does that make sense? In other words, with NOR, I can cancel out the inversion by using another NOR gate. In a NAND gate, I can do the same. I can cancel out the inversion by using another NAND gate. But you don't mix NAND and NOR and try and do the same. Does that make sense? Yes, no, maybe so?
Yes, ma'am.
Okay. All right. So one of the things they were showing you here, I'm sorry, I kind of jumped the gun a bit, was that they actually tied 2 of the 2 inputs together to create an inverter. To create an AND gate, they took a NAND, created an inverter, and got AND. Okay. To create an OR gate, they tied the signals together for 2 NANDs to create an OR gate, because this guy inverts the signal on the way out. And then they were able to do similar to create a NOR gate. Okay? If you're going to do it as a OR, if you're using a NOR gate, you tie the two signals together and you create an inverter. So similar things to what you just saw with the AND gate, the NAND gate, excuse me. So we have AND or invert gates for implementing sum of product expressions. We use PLDs for these as well. We'll go over these a little bit more in depth at another time. But the reason we do a lot of this is we're trying to minimize the number of gates and reduce circuit costs and size. So what do we mean? Well, it goes back to we now have the ability to use our watches as smartphones. We now have Bluetooth earbuds that are tiny. We want to reduce physical size of everything because the smaller it is, the more you can pack into it, right? Does that make sense?
Yes, ma'am.
So that's what allows our watches now to monitor our heart rate, monitor GPS. Some can play music. We can answer our phones and talk on them like a phone. When we became super spies, I don't know, but you know, I think everybody always wanted to be. I think it was Dick Tracy that had the watch. Everybody wants to be them, right? So not only that, it reduces the circuit's cost, which anytime you can cut cost, it's a good thing, but you always want to do it the right way. You don't want to create something dangerous. You want to create something that is useful and does what you want it to do. You reduce gate failures. So it goes back to that thing of the more you put into something, the more it can fail. The fewer things you put in something, the fewer points of failure you create, the better off the product and the consumer are. Okay. This can graphically, so when we do these mappings, we can show output levels for all possible input combinations, moving from one to another with only one of the variables changing. Like I said, well, I think they've got an example of it here in just a minute. So we create forms to do all this. It's kind of like if you remember doing the squares for DNA in school. It's similar to that. You're trying to just find ways to create these truth tables, to create what is going to happen whenever you start moving the power through these gates. So we use this to reduce equations and to implement the logic. And we use it to check for the design operation and make sure that it's going to do what we want it to do, because if it doesn't, then you can end up spending a lot of money trying to make it work or trying to figure out why it's not working. This is just kind of gives you a boost of, is this going to work? Is there a way that this could fail that could cause catastrophic issues? Okay, so this is how they start setting it up, and this is the different tables they start using to show you this. So it starts looking at signal A, and how is signal A put in? Well, it's going to come into a NAND gate, and it's going to come into an inversion before it goes to an OR gate. So it's starting to look at what are the pulses, what is the rate, and how is it going to signal output at the very end. Okay. So you can look at whatever inputs you need to look at to kind of sort this out. So a NAND gate is equivalent to an OR gate with inverted inputs, and a NOR gate is equivalent to an AND gate with inverted inputs. What they're trying to show you here is that an AND gate and an OR gate just about function the same way. So again, this is just all De Morgan's theorem. So I'm trying not to get too deep on some of this. A lot of this we'll be working on in class itself. So let's go ahead and go to summary. And I'll let y'all go just a little bit early today. Has everybody worked on their first week quizzes and agreements before we hit the summary? Everybody turned all those in?
I've done everything but that electrical safety test.
Yes, I'm trying to figure out why that is doing what it's doing. I'm going to have to delete it and reload it, I guess. So I've been fussing with it and trying to figure out what's going on with it. I'll hopefully have that out here this afternoon. Any questions, guys, before we go to summary? And then, like I said, I'll let y'all loose for the afternoon. All right, so several logic gates can be connected together to form combinational logic. There are several laws and rules that can provide means to form equivalent circuits. So kind of like if you only have, 24 NAND gates and you need a AND gate, or you have to figure out some way to create NOR gates from AND gates, you have different ways you can do this. What we're trying to always do is keep things simple so that it functions exactly like the original circuit, but without having other issues come with it. De Morgan's theorem is required in the reduction process if we are using inversion. NAND and NOR gates are sometimes referred to as universal gates because they can be used to form any of the other gates. Again, that only works if you're using strictly NAND or strictly NOR. So we also have different equations that can be done with these. You have and or invert gates used to implement sums of products equations. And then you have mapping that provides a systematic method of reducing logic circuits.